Let me now give you the general Gauss quadrature rule. So, we are talking about a rule with n-int number of quadrature points. So, L is the index and it goes from 1 to the number of integration points. Let us first talk about the weight. So, the weight is defined as by the following expression, 2 divided by 1 minus times the order, the derivative of the first derivative p prime of this polynomial. I will give you the expression in a moment. So, that is the weight, and the error r is actually twice raised to 2n plus 1 factorial of this raised to the 4, and in the denominator I have twice n int plus 1, and then the factorial of twice n int raised to the 3, and we are talking about the derivative. So, g comma xi 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 of xi bar, and this is 2n int. So, because we are using n int quadrature points, so in the error we are going to get the derivative which is of the order 2n int. Okay. What about xi L tilde? These are the quadrature points themselves. So, xi L tilde are roots of the Gender polynomials. P n int xi, and of course p prime n int is the first derivative. The polynomials themselves are defined through a relationship given as the following. So, this polynomial is 1 by 2 n int times factorial of n int, and we are talking about the n int derivative. So, that is the general expression for the Gauss quadrature rule, and by using different values of the number of integration points, one can actually derive these rules. So, these are mostly listed in certain textbooks. So, we do not have to do this explicitly when we want to use a quadrature rule. You can just look up in a handbook. So, for the 2-point rule, for example, the weights as well as the xi L tilde would be listed. Likewise, for third order, for the 3-point rule, 4th-point rule, all those would be listed and you can directly use them. What about multiple dimensions? So, Gauss quadrature in multiple dimensions. So, we are going to use the, just like we did for the Lagrange polynomials when we discussed the shape functions, we are going to use the rule in each coordinate axis and then do the expression. So, let us give an example in 2D and then we will generalize it. So, suppose I am to carry out an integral in 2D minus 1 to plus 1 g of xi eta d xi d eta. What I can do is I can leave the d eta integral as it is, the exact, and I can approximate the xi integral. So, I will approximate the xi integral and leave the d eta integral as it is. And for the integration along xi, I am going to use the Gauss quadrature along the xi direction. So, this is the expression I will use. So, my index now would be L1 because it is the first dimension. This will go from 1 to n int 1. So, the superscript here refers to that I am talking about the first direction, and this function g here is evaluated at the quadrature points. So, these are going to be xi tilde L with the index 1, but I am going to leave eta as is intact in the closed form, and then I would have to multiply this with the weight. So, this is the weight WL, but the index is, the superscript is 1, just to show you that indeed this is the first dimension. And just to make it more clear, I would add the 1 over there also and perhaps 1 over here, just to show that it is the first coordinate. So, this here is the expression. So, we have approximated the integral, the exact integral via Gauss quadrature along the xi axis. Next, what we can do is we can open up this integral along the eta axis. So, let us do that. So, this would again be an approximation, and now I would write an expression that L1 goes from 1 to n int 1 and L2 goes from 1 to n int 2. So, I can use different number of integration points along the xi and eta directions, and now my g function would have these evaluations xi L1 of 1, and likewise I can put the coordinates for the quadrature point for the second direction. So, these would go from L2, and I would multiply now with the weights. So, weights along the first direction as well as the weights along the second direction. Okay. So, that is, and of course, I will incur an error which I am not writing down because I have already put an approximation. So, this now is the Gauss quadrature rule applied to both the xi and eta axis. So, this is Gauss quadrature applied to both xi and eta axis. Okay. So, let us take an example. Suppose we want to use the 1 point rule. So, example 1, the 1 point rule. So, the integral I want to carry out is along xi eta, and this is my parent domain. Please remember the coordinates here are +1, +1, and the one on the left bottom is -1, -1. So if I apply the 1-point quadrature, then in fact this is the point where the quadrature lies, and my expression is the following. So -1 to +1, -1 to +1, g of xi eta d xi d eta can actually be approximated as, if I put in this expression simply L going from 1 to 1 and L2 going from 1 to 1, because it is a 1-point quadrature in each direction, then I would be able to see that this would be 4 times g evaluated at 0, 0. Okay, so I multiply the weights, and if you recall, the weight in each direction was 2. So the product of that gives me this 4. So it is very simple. If I just want to calculate this integral, all I can do is evaluate this function at the origin, multiply that with the weight, and I get an approximation to this integral. Suppose you are not happy with this and you want to use a 2-point rule in each direction. Mind you, now you can use a different rule in each direction. So suppose I have this expression g in which I have a higher order polynomial along xi and a lower order along eta. I can use different quadrature points. So let me just give you the example of a 2-point, so 2 by 2 point rule, which means I will apply 2 quadrature points in each direction. So let me again draw the diagram. So this is xi and eta, and a 2-point rule would give me these 4 quadrature points. Please remember that the 2-point rule in 1 dimension had these quadrature points related lying at plus minus 1 over square root of 3 along xi. So now they are distributed in this manner, and if I had to write down the approximation for this integral, then this would turn out to be g evaluated at this first point, which is minus 1 over root 3 minus 1 over root 3 plus a g times the weight, but the weight is 1. Okay, so in 1 dimension, if you remember, for the 2-point quadrature, the weight was 1 for both the points, so the product is also 1. Then I evaluate g at the second point, which is plus 1 by root 3 and minus 1 by root 3, plus the g evaluated at this third quadrature point, which is 1 by root 3, 1 by root 3. And finally, the last quadrature point, which is minus 1 by root 3. So a 2-point rule in each direction would actually give me 4 points in 2 dimensions. And if I extended this rule in 3 dimensions, then obviously I would get 8-point quadrature. Okay? And those are the weights. In this case, the weight is 1. So we can actually generalize this. So can tabulate the rule in multi-dimensions as the following. So we can say that minus 1 to plus 1, minus 1 to plus 1, g of xi eta d xi d eta. So instead of writing this horrendous expression that I have written here, for example in 2 dimensions, I can simplify this to a single array, and this would be given as just a single summation L going from 1 to the number of integration points G of xi tilde L eta tilde L W L. Okay. And this of course is an approximation, so I should put an approximation sign. So I can actually tabulate the same thing that is written over here as now n int is the total number of quadrature points. So if I am using 2 points along xi and 2 points along eta, then n int would actually be 4 in 2 dimensions. It would be 8 in 3 dimensions. So just to give you an idea, that n int would actually boil down to n int in the one direction times n int in the second direction. Okay. And similarly, my xi L tilde is given as xi tilde of 1 L of 1 and eta tilde L is eta tilde L of 2 and the second one. So, it is just a way of tabulating, and of course, W L is given as W L 1 times W L 2. So, I can just tabulate it in this manner and not worry about the indices along either direction. What happens in 3D? So, in 3 dimensions I can generalize this to -1 to +1, -1 to +1. Now, G is a function of xi eta zeta d xi d eta d zeta, and these I could just write it as summation L going from 1 to number of integration points, and the G is evaluated at the points, quadrature points, which are xi tilde L, eta tilde L and zeta tilde L, times the weight, which is W L. So, that would be the generalization in 3D. Okay. I just want to make a note here that the Gauss quadrature is not optimal in multi dimensions. We can show that the Gauss quadrature rule is the best you can do in one dimension. Unfortunately, the way we have applied it in multi dimensions, it no longer is optimal. You can actually find better rules, but obviously they are a little bit more complicated, and therefore Gauss quadrature still remains the most popular choice. In fact, in multi dimensions, it is extremely difficult to find the optimal rule. Okay, so research is still going on to be able to nail the optimal rule in numerical integrations. So, as far as the finite element community is concerned, the popular way of doing the numerical integration is the way I showed you, use Gauss quadrature along each dimension and then generalize it the way we have written it over here.